Good morning, everyone, and welcome. I'm Adnan Akhdar, and I'm excited to have you all here today. Thank you for taking the time to join this session. Today, we'll be discussing the use of CFD simulation as an essential tool to design smoke control systems for large and conventional spaces. I do hope that you find the presentation valuable and the information relevant and pertinent. The presentation will last about 15 minutes and it will be followed by a Q&A session at the end. Feel free to take notes and ask questions throughout the presentation, either via chat or during the Q&A. Before we dive in, let me walk you through today's agenda, so you know what to expect. First, we'll start by discussing the purpose behind the presentation, and we will highlight the challenges that we usually face when dealing with smoke control system for large and unconventional spaces. And we will highlight those challenges, and we will also showcase how we have been using CFD simulation tools to solve them. Next, I will give you a brief overview on who we are as a company, our background, and our expertise. This will provide some context for the solutions and insight we'll be sharing today. Following that, we will delve into the use of CFD as a design tool. Then we will move on to some real-world case studies, and we will showcase two of our challenging projects where we have been able to use CFD to successfully, optimize the smoke control strategy, noting that the solution that was developed would not have been possible without simulation tools. Lastly, we will have an open Q&A session where I will address any questions or thoughts that you may have. Feel free to jot down your questions throughout the presentation. So, what is the purpose of today's presentation? As we all know, buildings in modern architectures have become a lot more complex, a lot more interconnected. And as a result, designing smoke control systems for these types of spaces have become a lot more complex when it comes to predicting smoke propagation. So as a start, we will try to highlight, the challenges, the unique challenges that are posed by those type of large and unconventional spaces. Also, we will highlight how CFD modeling has become essential as a tool to solve those challenges by helping us predict smoke spread, determine airflow patterns and temperature changes and stratification patterns. Also, we will show how we have been able to leverage CFD simulations to help us optimize our designs and determining, for instance, the location of vents, fans, smoke barriers, to effectively manage smoke movement and enhance overall. So, why is it challenging to manage the smoke release in large and unconventional spaces? The main challenge, as a starting point, is definitely the geometry factor. Basically, due to the geometry, it's very complicated to predict how smoke will be moving. The second challenge is smoke stratification. So, in complex geometries, there might be stratification occurring at different levels, and as such, any smoke control system that needs to be designed will have to handle different temperatures and densities at different levels. This is especially prominent in case of balcony-filled plumes. So this is using conventional methods. It's very hard to predict where smoke will stratify and at what level. CFD, as we all know, can basically help us tackle most of those challenges that we just highlighted. In fact, we can, using CFD simulation, model complex smoke and heat behavior, and this will provide us with insights on how smoke will move and stratify. These insights can help us, optimize the configuration of the exhaust and makeup air provisions. It can help us develop validated and tailored smoke control solutions that address the unique challenges of the specific building in hand, rather than relying on one-size-fits-all approaches. Following slides, we will just give you a very quick overview on who we are before moving on to the case studies. Akhdar was founded almost 70 years ago, and it is part of the Sidara collective, which is also founded. We are a multidisciplinary consulting organization, and we have 5 principal design centers and 54 permanent local branch offices. Our market sectors are diversified, and they include buildings and cities, transportation, water and environment, projects and facility management, as well as digital solutions. Our in-house expertise also covers a very wide range of engineering fields, as shown. As a firm, we are committed to service excellence and have been consistently ranked among the top 10 consultancies by Engineering News Record for over 30 years now. For instance, we are currently ranked 4th among pure design firms in the US. Let us now move on to the case studies. The first case study will highlight the importance of properly sizing the smoke reservoir and also of properly configuring the makeup air position. The current slide will also help us showcase the importance of the smoke reservoir and its relationship to the exhaust rate. We face a lot of issues with architects and with stakeholders where they believe that simply providing the exhaust fan should be sufficient to control the fire or to control the smoke released from the fire. And most of the time we show them this slide. We show them the relationship between the size of the reservoir and between the required exhaust rate. And this is the numbers that we are showing here are only for presentation purposes. But basically they show the inverse relationship between smoke reservoir and the exhaust rate. The bigger the smoke reservoir, the smaller the extraction rate that would be required, the smaller the makeup air required. The building in the current case study, and as we can clearly see, is not conventional. It's an atrium with 4 levels connected, level 0, 1, 2, and 3. We have used CFD modeling to optimize the smoke control strategy. In the first model, we had a fully open space without any kind of compartmentation and with minimum makeup air provision. Basically, the architect gave us a lot of headaches and were not very flexible in providing the requirements. Upon failure of that model, we were able to, let's call it, coordinate larger makeup air provision. However, even with these larger makeup air provisions, we found that a much bigger smoke reservoir would be required. And so, based on the finding of the second, we required, in addition to the makeup air, to provide smoke curtains at the upper floors, level 2 and 3, to increase the smoke reservoir. In the current slide, we show the curtains that we have proposed following the findings of the second. The current slide basically shows the configuration of the CFD slides shows the findings from the first two models, models 1 and 2. In model 1, we had an extraction rate of almost 50 meter cube per second and a makeup area of 6 meters squared. So as we can see, makeup air speeds were very, very high, and as a result, the rising smoke plume was significantly disturbed, and tunability conditions were compromised at the upper floors at very, very early stage. In Model 2, we were able to provide a larger makeup area, and we were able to increase it from almost 8 meters squared to 33 meters squared, and with the same extraction rate of 50 meter cube per second. While there was an improvement in the rising smoke plume behavior, we could still see that tunability conditions were compromised at very early stages on the upper floors. Actually, if we look at the animation, we noticed that smoke was compromising level 2 and 3 at the very, very early stages. And we also noticed that the smoke plume is plus or minus dilute at the smoke interface layers, and it's almost dilute. We notice that the colors in the smoke interface layer is like greenish. This means that there is a lot of turbulence and a lot of mixing occurring, which is not something that we actually want as part of the findings from Model 1 and 2 indicated that, in one hand, the makeup air provision was not sufficient and that it needed to be increased. And in the second hand, it also indicated that the smoke reservoir was not sufficient and that it needed to be increased. So in Model 3, we were able to provide additional smoke curtains at the upper floors, which increased the smoke reservoir. And we were able to control the smoke release and maintain tunability condition with an actual reduced extraction rate of almost 40%. In the current slide, we can clearly see that a very stable and smooth rising smoke plume was achieved. The same observation can be made in the current slide, which show that makeup air speed reaching the fire as less than 1 meter per second. As a summary of findings from the current case study, we can actually make two important points. The first one, which is the importance of having a properly sized smoke reservoir. Properly sizing the smoke reservoir would actually help optimize the makeup air requirement as well as the extraction rate. And we could see here that in Model 3 we could achieve tunability conditions on the upper floor with a reduced extraction rate of 30 meter cube per second instead of 50 meter cube per second. Also, the second very important point, which is the balanced makeup air provision. Without a balanced makeup air provision, it is very, very hard to actually properly control the smoke release. The second case study will focus on the importance of controlling the width of the balcony spill plume. This is a very effective strategy to optimize smoke control systems, actually, because it helps us reduce the exhaust requirements significantly, actually. The corresponding makeup air demand is also reduced. By reducing both the makeup air demand as well as the exhaust air requirement, we can also have a much simpler design which has a lot less space. In the current case study, we will look at an auditorium with a stage. Okay, we will compare three models. All models have the same makeup air provision and the same exhaust air provision. And the only difference between them will be how the smoke control system is configured to achieve tunability conditions. The current slides showcase the geometry of the auditorium and stage. In the first model, the stage and auditorium are connected. The results of the first model indicated significant air activity in the volume. As we can see, there is a lot of air moving, and the smoke plume is slightly pushed towards seating areas. And also we can see that there is a lot of air coming from the stage area, which is not something that is actually preferred. As a result of the significant air activity in the space, there is a lot of mixing of the smoke plume, and we can see that the tunnelability conditions are compromised on the upper level. So in light of the findings from the first model, we decided to actually separate the stage area from the auditorium area completely, so that there will be no more air coming from the stage area pushing the smoke plume. And as we can see in the first picture, the smoke plume now is riding smoothly without being pushed back toward the space. However, we also noticed that the stratified smoke layer is very dilute, and visibility is around 5-6 greenish, basically greenish colors. So it's not the dense smoke plume, and this indicates a lot of mixing and a lot of air activity. And as a result, tunnelability conditions are still compromised on the upper floors, as we can see in the next slide. As mentioned previously, tunnel conditions are also compromised on the upper floor, even at very early stages, because of the significant air mixing or smoke mixing occurring in space. Based on the findings of the previous two models, we could identify that one of the big issues is the large volume of smoke that is being generated by the plume. So by limiting the width of that plume, we can theoretically reduce air activity in the void. The findings from Model 3 actually confirm our expectations. So by reducing the width of the plume, we were actually able to reduce the volume of smoke spill. As we can see, the volume of mixing now has significantly reduced. We can see that there is a thinner smoke interface layer that is now much denser around. As seen in the current slide, tunnelability conditions are now maintained at all times during the simulations, even at early stages. As a summary from our second case study, we can see that a successful smoke control strategy could be achieved by simply reducing the width of the balcony spill and by improving makeup air delivery by separating the stage area from the auditorium area. In conclusion, we hope that we were able to highlight the importance of using CFD simulations to deliver optimized smoke control strategies for large and unconventional spaces. We would like to highlight that as Akhdar, we have been using CFD for over a decade, and we strongly advocate for its early application in design to reduce risk and enhance fire safety. Thank you for your time today. We can open now the Q&A session.
Hello. I can't see you, so welcome. Let's see here. I appreciate the talk. That was great. There's a question online. It says, were there any sensitivity studies in different growth rates or fire locations?
Actually, that's a good question. Indeed, as part of the design, what we are showing you here is what basically we call the butter. This is the summarized version. But it was a long process. Indeed, we test different fires, we test different capacities, different growth rates. As part of the process, we have to analyze what kind of material can burn. So yeah, there is a big process going on in the background. However, we are just showing let's call it the butter, the end product.
Okay. Let's see. Questions in the room? Got Kevin here.
What type of CFD model was used in the study? Like a large eddy simulation or a RANS model?
No, we used the LES model, the default was in FDS. We did not play with the modeling parameters within the model itself from FDS.
Oh, okay. In order to visualize the results, is that the PyroSim viewer?
No, that's not Python viewer. That's a tool that we have where we can extract different levels and just plot them.
Oh, okay. Thank you.
Thank you.
Any other questions in the room? There's a question here from online. Was wind impact considered?
Actually, no, because we have like a closed space, and basically we don't have any direct exposure to wind. So in that case, since this is an indoor space with little communication to outside, it's only connected to maybe lobbies and corridors. So there is no direct wind effects on the model itself.
Okay, great. Any other in the room? I don't see anyone. It's hard to see, but I don't see anyone raising hands. So thank you very much for joining us and the presentation. It's really interesting work. So thank you, and we'll see you soon.
Thank you. Have a nice day, everyone.